Yeah, example is, sorry, if we are investigating the influence of people is a factor. Ambient outside temperature is another factor. So here we have two factors, number of people and outside temperature. What are levels? Levels are values which these factors might take. For example, if you look into number of people, minimum is 2, maximum is 40. So we have two levels. Outside temperature, low and high, right? You have two levels. However, if you have a center point or some other point, 30 degrees, then we can say that we have three levels. What is a treatment? Assigning a level to a factor is a treatment. For example, number of people is equal to 0. So to a factor called people, I'm assigning a level called 0. Then it is a treatment. Number of people is equal to 40. Then I want to do an experiment based on that. That means what are you doing? You are assigning a level called 40 to a factor called people. In this particular experimental run, this is called as a treatment. Then treatment combination. Treatment combination means the combination of respective levels of input variables for an experiment. For example, look at this. If we conduct an experiment with 40 people at 20 degrees, then that test would be a treatment combination. I'm combining two things, right? The other combinations could be 40 people at 40 degrees, 40 people at 30, 0 people at 20. So I look into all the permutations and combinations basically. Right? That is treatment combination. Then number of treatment combinations, how do we arrive at that? How do we arrive at that number? Right? Let us go to this example. If there are three factors with 2, 3 and 4 levels respectively, then the total number of treatment combinations would be, just multiply those levels, you'll get the number of treatment combinations that are available. If all factors have the same levels, that means I have people, I have two levels, 0 and 40. I have temperature, I have two levels, 10 degrees and 20 degrees, right? I have some other factor which has two levels. If everything has two levels, then that is 2 multiplied by 2 multiplied by 2, which is 8. Next thing is blocking. Blocking means you run multiple experiments in one go in a block. For example, if I have 8 tests to be performed, 8 experimental tests, then what do you mean by block? Block means probably I'll run first test, fourth, sixth and eighth test as one block in one go. And probably 2, 3, 5, 7 I am going to run as block 2. Then I have center points. If we only test a model at two extreme points, that is if I test a model at 0 degrees and 40 degrees, then always this particular line would be linear. Linear means a straight line, right? This model will not tell us if the model is not linear or not. Anytime, even if a model is in reality non-linear, if you're using only 2 points, two extreme points, then you will see a linear model, a straight line. But the moment you try to introduce a third factor, for example, instead of 0 degrees and 40 degrees, what I want to do is I want to introduce something called as 20 degrees centigrade. If I do this, now the model might change. It might look something like this. It might look non-linear if I erase this line, right? This is not a straight line. So in this way, the moment you introduce a center point, you'll come to know whether the model is non-linear or not. It need not always be non-linear. Sometimes if you have 0 and 40 degrees, right, and if you take a midpoint that is 20 degrees, and if that also is falling on the straight line, then it is a linear model. It's not a non-linear model. So introduction of a center point or a midpoint will just tell you whether your model is linear or non-linear. That's it. Right? It need not always be non-linear. Next thing is repetition. An experimental run is conducted several times for the same treatment combination. to neutralize the effect of any uncontrollable unknown factor. Oh, did I lose my audio? 1 second. Yeah, a recap, right? I have started that. So if you're going to conduct an experimental run several times using the same treatment combination, where did I go? Okay, 1 second. Okay. If you conduct it several times for the same treatment combination to neutralize the effect of any uncontrollable or unknown factor. For example, if I'm going to run multiple experiments, not just a single run for people, 40 people with 0 degrees, 40 people plus 0 degree centigrade. If I run it once, fine. But if I run it multiple times or several times, what happens is, if there is any issue with some other unknown factor which you're not considering, that will be eliminated or neutralized. Right? This is because I don't know about the humidity factor. Is it impacting my air conditioner conditions or not? I really don't know that. So the moment I run experiments multiple times using the same treatment combination, I get to see various values. Because of those various values, the effect is going to be neutralized. That is all about repetition. Then what is replication? Conducting repeated experiments at the same experimental conditions. When replication of a design is done, the complete set of runs from the initial design are duplicated. So you have to ensure that all the other parameters or the conditions remain the same because you're replicating it. You're not repeating it. So that is the difference between repetition and replication. Then you have mains effect. The effect which is observed in the response variable. What is the response variable? Your y. Yeah, the effect observed in response variable on changing a single factor from one level to another level. For example, the main effect of changing the number of people is that if the number of people increase by 1%, then the air conditioner performance drops by 3%. So this is a main effect. What is the interaction effect? The combined effect observed in response variable on changing the specific levels of 2 or more. Example is, if the number of people increase by 1% when the outside temperature is hot. When the outside temperature is hot, the performance drops by 4%. But when the outside temperature is cold, then the performance is not impacted. So this is a combined effect observed in the Y variable, response variable, on changing the specific levels of 2 or more factors. If you are changing one single factor from one level to another, then it's main effect. If you're changing the levels of 2 or more factors, yeah, that is when it is called as, it's telling something, but yeah, still I'm on. Okay, let us move on to the next thing. What are the various types of experiments that we have seen? One is the trial and error, which we most commonly use, right? We randomly change the inputs and see what is the impact on the output. And we do not have any specific plan as such. We just go ahead. Let me try this. Let me try that, right? Whenever you're going to a new location on a vehicle, sometimes you do trial and error. Let me go this way. Let me see whether I can reach the destination or not. So that is trial and error. Next thing is OFAT. One factor at a time. You vary each factor one at a time to understand the impact of that variable on the output. So in y is equal to f of x, right? In the example that we were seeing the air conditioner performance, that is y, based on number of people and the outside temperature. If you change just the number of people and see what is the impact on y, that is one factor at a time. If you change just the if outside temperature changes and then if you see what is the impact on your output, that is called one factor at a time. Then we have full factorial design. Running all the possible combinations of factors in order to develop a complete model of the system. For example, if I have 40 people and if I'm running at 40 degrees centigrade, if I have 40 people, if I'm running at 30 degrees centigrade, 40 people, I run the experiment at 20 degrees centigrade, 40 people, then 10 degrees, then 40 people at 0 degrees, then I change 20 people at 40 degrees, 20 people at 30 degrees, 20 people at 20 degrees, so on and so forth. So if I'm going to run each and every experiment in this way, it is called as full factorial design, running all possible combination of factors in order to develop a complete model of the system. But as and how the number of factors increase, it would become cumbersome and rigmarole to actually calculate these things. So we go ahead with the fractional factorial design. What do we do in this fractional factorial design? Running only a subset of the test. Suppose I have to run 100 experiments, 100 runs with full factorial design. Then your fractional factorial design might say, don't run everything, run 8. Yeah, the quality or the kind of results that you get by running full factorial cannot be replaced by fractional factorial design. But yes, if you do not have the time, energy, money at your disposal, this is what you do. You do fractional factorial design. You run only a subset of tests, and still you'll be able to derive some meaningful information from those tests. So fractional factorial, whenever you have more than 4 factors, just as a thumb rule, that is when you try to use fractional factorial design. It identifies the interaction effects, main effects, and also few interaction effects, not all the interaction effects. Full factorial, when you have 5 to 1 factors, that is when you try to look into the relationship between the various factors, and this design of experiment type looks into all means effect and interactions effect, all the effects basically. DOE phases. DOE can be used for screening or for model characterization and optimization. What do you mean by screening? Basically, DOE is used for 2 reasons, right? One is screening and another thing is characterization. What do you mean by screening? Selecting the most important inputs from a long list of potential inputs. Yeah, you use highly fractional factorial experiments. Then you have characterization. What do you mean by characterization? You develop a model between y and x, which can be used for optimization. You use nearly full factorial experiment when you want to do characterization. When you want to do screening, you use fractional factorial experiment. Look at this for an example. Number of factors, if we have 4, the maximum runs for full factorial would be 16. The maximum runs for screening the design, just checking whether the design is good or not, is 8. Number of factors is equal to 7. If it is 7, the maximum runs for full factorial is 128. Maximum runs would be 8. So if the number of factors are 11, then you will have 2048, that is 2 to the power 11, right? Those many runs. But minimum number of runs that would be required are 12. So in this way, if you see, simply speaking, your full factorial is going to increase tremendously, exponentially, as and how the number of factors increase, right? But if you look at your fractional factorial design or maximum runs required just to screen the design, those are pretty less, very less. There is a huge difference in running 32 experiments versus running all the experiments. 214 crores, 74 lakhs, 83,648 runs is what you require. 214 crores, 200 odd crores of experiments you have to perform. Is it possible? Be very, very cumbersome, right? So hence you resort to this maximum runs for screening the design concept. And design of experiment need not always be adopted by everyone, right? There are few hiccups when you actually get started with design of experiments. We've always studied one factor at a time and it works. Why should we learn something new? This is the attitude of the people which kills the design of experiments or innovation, right? So few people say that we already know everything. We know the problem, answer, everything. We don't need to use this tool. We just need to fix the problem is what people think. If real life was that easy, this simple, then all the businesses would have become super success. That is not the case, right? Majority of the businesses fail because of this attitude. Few people say it costs too much to do this exercise. Again, all right. Sometimes not sure why this has happened now because I'm using dongle maybe. Okay, sometimes you do not have management support. That also could be a reason. People are not going to give us the luxury to actually perform these design of experiments. That also could be another reason, right? Few people do not have the knowledge of what design of experiment can do to you, right? So that could be another reason why, they would say that, no, don't do this crap work, kind of, right? So design of experiments should be followed in a structured way. What is the structure that we have to employ? You define what is the objective of the study. What is the output variable? What are your goals? What do you want to achieve actually using this design of experiments? Then comes brainstorm, right? You try to brainstorm to identify what are the potential factors. You identify who are all the appropriate team members. And then you try to shortlist all factors that are controllable. For example, if you consider, or if I ask you a question on, what are the various things that your mileage of the car will be dependent on? It will be dependent on, you might say, car engine capacity, you might say on the horsepower, you might say on the chassis, you might say on the air pressure of tires, right? And you might also say that it depends on the road conditions, it depends on the driver who is driving, etc. Road conditions and driver who is driving, is it under your control? No, it's not under your control, right? So these kind of uncontrollable factors can be eliminated, right? You brainstorm and identify those factors on which you can have sufficient control on, and something that can be easily changed. For example, air pressure, yeah, you can easily change. Right, in this way you have to select what are those controllable factors and what are those things which can be easily changed. Next thing is select levels of input variables. Initially you select a wide range that is practical. Input range, right? What are the various inputs, right? Levels basically. That means if I have temperature, you select a broad range. Let me do it from 0 to 40 degrees. You select a broad range initially. That is what you will have to do. Then select the design that best fits the study. Do you want to perform full factorial? Right, there are conditions that we have already discussed. When do you do full factorial? If you have the factors, number of factors which are between 1 to 5, right? If it is greater than that, then you'll most probably opt for fractional factorials, because you cannot, keep on conducting the experiments, running the experiments, right? You need to somewhere stop. And then you create the design. You randomize the test. You do not do it in an order like 40 people 40 degrees, right? Then 40 people 20 degrees, then 40 people 0 degrees. In this way, you do not perform at each level or in a particular order. You try to randomize it. By randomizing, you try to eliminate the influence of noise factors. If at all there are any noise factors, you try to get rid of those noise factors. Then you actually conduct the experiments and try to collect the results of those experiments. and always ensure that the test settings are accurate and tests conducted are according to the design. Yeah, they are not performed without any prior thinking or logic. It has to be conducted according to the design that you have adopted. Then you analyze the data and draw inferences. You determine the optimal input settings for the best response. When will I get the best mileage of the car? When my engine capacity, air pressure, horsepower, the chassis, weight of the vehicle, everything is correlated, right? Everything is, supporting each other, complementing each other. That is when you get the best response. Response is always Y. Predictors means X, right? Then present the practical conclusion to stakeholders using some kind of graphs. By running the design of experiments, you'll be statistically able to prove something. But we don't just want to statistically prove something. We want to have a practical solution which can be showcased to the senior management. Then here is your fractional factorial design. In a full factorial design, you can estimate all the mean and interaction effects. For example, if I have three factors A, B, C effects are called as main effects. Interaction effect is when two variables, the two factors try to interact with each other. For example, AB, right, is one factor. AC is another factor. BC is another factor, right? ABC is a three-level factor. So in this way, you have third order factors and all that. Then let us look at fractional factorial design. We don't run all possible combination of tests because we know that, we are going to waste a lot of time. So we sacrifice some ability to estimate, and then we do only a fraction of the full factorial design. For example, we can only estimate the combination A along with BC, B along with AC, and C along with A. We call this a resolution 3 design because we have three factors. You call it as resolution 3 design. But look at this. The main factor A are mixed with the second level factors. So they cannot be independently estimated. That cannot be done. And for a resolution 4 design, the main effects would be mixed up with, the main effect A is mixed up with third order effects, that is B, C, D, etc. Now, assume two variables. We have temperature and concentration with two levels each, low and high, right? How many factors we have? Two factors. How many total number of runs we can have? Because each factor has two levels, that is temperature also you have low and high, and concentration also you have low and high. So it will be 2 raised to the power 2, which is 4. How many main effects can you have? One is A, another is B. So you have two main effects. How many interaction effects you can have? A, B put together. Simple. Consider this. How many factors do we have? 3 factors. What are those? A, B, C, temperature, concentration, and catalyst, right? And for each factor, you have two levels, -1, +1, -1, +1, -1, and +1. So we have 3 factors and 2 levels each. Hence, it will be what? Levels raised to the power factors. 2 raised to the power 3. Yeah, absolutely. Then you'll get 8. What are the number of main effects that you can get out of this? These 3? One is A, one is B, another thing is C. How many two-way interactions you can have? A, B, B, C, C, A, 3. How many three-way interactions you can have? A, B, C. Again, you should not say A, B, C, B, C, A, same things should not be repeated. That would not be considered as another interaction, right? You'll have only one interaction, A, B, C. Things which are interacting with each other. If you're mixing 3 chemicals, for example, you're mixing 3 chemicals, job is done, that's it. You cannot remove those chemicals again from the mixture, and then you cannot say that, now let me first combine the second chemical with the first, so on and so forth. That would be difficult. Now, what is a balanced design of experiment? design in which the number of runs are same for each level of the factor. For each level, that means for -1, I'm going to perform 4 experiments. If you see this table, there are 4. For temperature, with -1, I'm performing 4 experiments. -1 means low. And with +1 also, I'm performing 4 experiments. +1 means high. Right, so they are balanced. With -4 I'm performing 4 and +1 I'm performing 4. If you look at concentration also, you will see 4 -1s and 4 +1s. -1, -1, 2, 3, 4. 4 -1s and 4 +1s. This is called as balanced design of experiments. Even if you see catalyst, you will see 4 each. 1 -1, 2, 3, 4. I have 4 -1s and 1, 2, 3, 4. I have 4 +1s. So once again, there is equal distribution. And also in this balanced design of experiment, the sum of all these numbers would be 0. You can just check that. So this will be -4 plus 4, 0. -4 plus 4, 0. And here also you'll get 0 if you try to sum up everything. For a two-factor design, there will be 2 runs for A at high level and 2 runs at low level. Similarly for B. Check if the signs of AB is also 0. Okay. So AB, -1 and -1 is +1. -1, -1 would be +1. -1 and -1, +1 would be -1. So you know this, right? Negative and positive would be giving you negative. Negative, negative would give positive. Positive, positive would anyways be positive. Even if you look into the combined effect, the interaction effect, once you calculate that and sum up the numbers, once again it would be 0. That is what is balanced design of experiments. How many ever interactions you look at? 2-level interaction, 2-way interaction, 3-level interaction. So the values would still remain the same. Yeah. Now for the data below, let us calculate the main and interaction effect. Main effect means for A, for B separately you'll have to calculate. How do you calculate? Sum of plus, sum of minus divided by number of plus. So they're telling, look, take the sum of plus sign, that is 122 plus 141, subtract it with the negative values, that is -1 and +1, -1. -1, one value corresponding is 102, another value is 88. So 102 plus 88 divided by yeah, I mean, in fact, we can just stop after this then. Divided by 4, because there are 4 levels, right? We have 1, 2, 3, 4. So if you do that, you will get the main effect of A. Or in that way, you can also calculate the main effect of B.